This is the beta lesson for 5-4. So, fundamental theorem of calculus. This is the alpha lesson. In your textbook, page 294. What happened? If you meet the criteria, which is these variables match, you're taking the derivative of an integral, and the lower limit is a constant, you're going to get back to the parity. The beta lesson is the fundamental theorem of calculus part 2, which is saying this. This is the derivative, and you're anti-differentiating. So what does this mean? The sum of all these rectangles that are that tall and that wide. We take you to the parent graph of B input, subtract the parent graph of A input, is telling you the area under the derivative corresponds to delta y of the parent graph. So your H chart would look like this. Each philosophical, hear that? So, your parent graph looks like x, f of x, being f of x. Well, that's confusing. It's just another way of writing the derivative. It's f of x. So, to distinguish that from the parent graph, we're saying capital. Right? You have to get on board because that's the way it's written. I mean, if you want to just say, I'm anti-differentiating f prime of x, you are doing that. But it's giving you the change in the height of the parent graph. So, the A and B children are having their 4th test today. And they're just starting chapter 5. So they're just trying to get their mind around this, that we have left differentiation, we are into anti-differentiation. That's the most important distinction you have to make for you make. Am I asked for the instantaneous? Am I asked for the slope of the curve? Or am I asked for the area of the curve? So here's example 5. One page. 300. Evaluate this using an antiderivative. So we're going to do the power rule in reverse. So you think of this as x cubed plus 1 is the derivative. And we want to take the area under the derivative by anti-differentiating. We want to add up all those little rectangles that are x cubed plus 1 high and dxy. So what would happen? To do the power rule reverse, you replace this 3 with 4. Because the power rule is, rewrite the exponent in front of the variable, and then replace the exponent with 1 less. So you're multiplying and then adding -1. But if we're undoing it, we undo the reversal operation. So we undo subtracting 1 first. So we add 1. We get 3 plus 1. And then instead of multiplying that back, we divide. 1 would give you an x. Then you back up and say, okay, I want to make sure I did this right. I differentiate, so take me back to the question. 4, reduce it with the 4, that gives you x to the 3rd, derivative of x is 1. From these two values, so I put, ready? 3 in here. I would get 3 to the 4th, 81 fourths, plus 3, which is 12 fourths. Subtract, put a -1 in there. And you would get 96 fourths, which is 24. Okay, what does the 24 mean? It means that's the change in height of this parent graph between -1 and 3. So if I go over here and say -1 and 3, what's happening here? For the parent graph, you're getting 1/4 take away 1, you're getting -3/4. And then you put 3 in there, and you're getting 93/4. So 93/4. That change from here to here is -3/4. The change there is 96/4. That's how much the parent graph went up. So I drew this picture. And I put the parent graph. What did I got? 2x to the 4 divided by 4. So we'll put it on here. Here's what the picture would look like. I have to edit that because I put the wrong thing in. So you get a y equals, and I type x carried 4 divided by 4 plus x. Now what did I do? I said plus these brackets, and I put in the constant. Remember, this is the Pringles. -2, comma, -1. Comma 0. So it's going to draw these graphs one after the other. They're all sitting in there like that. There's your Pringles. But what's the difference? If you go here, I said, okay, let's do, let's start at -1 and make our delta table 4. So we're going to jump from -1 to 3. Ready? There it is. -2.75 to 21.25. Okay, it went up 24. It went up 24, which is what you got when you found the area under the derivative. It's giving you the change in the height of the paragraph. See, it doesn't matter. This is with the constant of 0. If the constant gets added in, then this goes up by the constant, so does that. The difference is still going to be 24. So there's a typo on this thing. I just have x to the 4th plus x, and it should be x to the 4th divided by 4. It doesn't affect the answer. It changes 24. Okay? So that's your model. We're going to pause this. You're going to problem number 29, please. All right, so 29 would look like this. It's giving you practice with the power rule in reverse. So this 2 becomes a 3 divided by 3. X squared goes to x cubed plus 3. 1/2 plus 1 is 3/2. Divide by 3/2 is multiplied by 2/3. Put 1 in, then put 0. Now, gotta be careful. The lower limit is 0. you still have to put 0 in. You can't get complacent. So now the lower limit is 0. So I'm just going to calculate this, and the upper limit is always going to be subtract 0. It's not. You might have a mu here. This could be x plus 1 in the parentheses. So it's not necessarily going to generate a 0. It does in this case. So that's telling you 1, which means what? This is the derivative. The area under the derivative from 0 to 1 is 1, which means delta y of the parent graph went up 1 between 0 and 1. Now, we're going to move to, well, example 7 is just a calculator question. I'm looking at example 7. It says, there's a picture on page 301. Type that in there, and what? You would get a 0. Why? Because the graph's symmetric about the x-axis. If you wanted the total area in there, you would use absolute value, and it would reflect, you see that picture on the margin, page 301, it will reflect everything that's in quadrant 3 and 4 up into 1 and 2. So the absolute value gives the prompt, okay? And then there's a problem for you to do. Example 7, or problem 51, which we're not going to do, but here's the reference for it, which is the old operating system. I put in math 9, the absolute value of a function, dx negative 2 to 2. And what happened? That made the area below the x-axis get reflected above the x-axis. So you get the total area, not the negative. Now, 8 is more important. In fact, it's very important. And you notice this so far, that the assessments are heavy on pictures. Well, you're not going to bluff your way through a picture course. You have to understand concepts of what's being asked. So here's what we got. H of x is the integral from 1 to x of f of t dt. So h is the parent graph, right? And then we're going to anti-differentiate. We're going to add up all the rectangles that are f of t total dty to get this. Right? And you get the picture in the margin on page 301, which is on the PDF. So that is the graph of the derivative. We want the area under this. So the first thing says, what is h of 1? We don't have a picture of h. That's the parent graph. So we put 1 in here as the upper limit. What do we get? We get a 0. So why don't I go over here and say, here's what I get. I have x, I have h of x, and I have f of t, let's call that the derivative. Okay? If you put 1, the parent graph is a height of 0. Because you have no width, you want from 1 to 1. Okay? How about h of 0? What is h of 0? Now this is the whole reason we're doing this. To the left of 1, see this begins in 1. To the left of 1, the graph of the derivative is above the x-axis. Yes? What does that mean about the parent graph? If the derivative is positive, what's the age of the parent graph? Huh? It's increasing. So it's increasing between 0 and 1 to get to 0. So it must have been negative. Does that make sense? And that's where you change, that's the property where when you invert it. So if I say, okay, if I go from 0 to 1 from f of t, that area, that's equal to the opposite of 1 to 0 of f of t. Yeah, we did that. We said, okay, we understand it. We changed the limits, we changed the SIG in. That's why. Because this thing starts at 1. So if I go the other direction, the derivative is positive. So the area is positive. But that meant the parent graph was rising. So whatever that area is, we have to subtract it from 0. Does that make sense? It's not going to make sense to start the first time. I'm going to think this through. The most important problem up here is big. If you have to come back to that multiple times, you do that. You will absolutely get a question that looks like example 8 part B. Next thing, local max. Where's the local max of this graph? Well, that's not the way at home. Are you ready? It happens at 4. Why? Because the parent graph is going up between 1 and 4. Then it begins to go down. So the local max is 4. Where's the local min? It's at 8. Because the graph is going down till you got to 8. Because the derivative is below the x-axis. And then where are the inflection points? Ready? So, this was a question that was on, I guess it was your 4 assessment. The inflection points. Well, what about the inflection points? That's when the second derivative is 0 fails to exist. Yes? We have a picture of the first derivative. So we have to find out where the first derivative would have a horizontal tangent. Because if the first derivative has a horizontal tangent, then the picture of the second derivative would have a slope of 0, so it would be a 0. Watching this? We want the derivative of that graph to be 0. So the derivative of that graph would be 0 when you have a horizontal tangent. 1, 3, 6. Confirm the sign change, decreasing, increasing. Increasing to decreasing, decreasing to increasing. Those are the inflection points. That, ready? That problem, which we're going to move on as a model to 57, but you can't cut corners on this. If you can't answer 57 today while we're sitting here, then there are the problems you need to focus on. You need to focus on the pictures, because you're having a big picture conceptual issue. So that's up there. You go to 57. For 2 minutes. $58. What do you get? This is a picture of F. H is the parent grid. So you want H of 0. Well, it's the same thing as in the example. Because the initial value is 0. So you get a 0, 0, you have to go with. Right? How is H behaving from 0 to 6? It's increasing because the derivative is positive. What's the cavity between 9 and 12? Well, ready? That is a layered question. Because they're asking about the second derivative. And everybody can answer that question if they have a picture of the second derivative. You don't. You have a picture of the first derivative. So for C, the answer is between 9 and 12, H, the parent grid, is concave up. Why? Because this derivative is going up, which means the second derivative would be positive, would be above the x-axis, and that would confirm that the parent grid is concave up. But you ever seen how you easily get lost in here and mixed up? You get a picture of the first derivative, and they ask you something that's in the second derivative, and listen, or about the parent grid based on the second derivative. H of 12. Is H of 12 positive or negative? H of 0 is 0. And this area in quadrant 1 is greater than that area in quadrant 2. So H of 12 has to be positive. Or quadrant 2, not 2. This area 1 is bigger than the area 4. So H of 12 will be positive. The local max occurs at 6. Because it's increasing from 0 to get to 6. You've got to be careful because that is the trick question. Where's the local min? What are you going to say? You're going to say 12. Yes? Wrong. Why? It would be at 0. How come? Because at 0, the parent grid is going up to get to 6. Then it's going down, but it didn't go down as much as it went up between 0 and 6. So the minimum value would be at the end point. So if you're kind of like sleepwalking through this, you say, oh, okay, well, I know the mid's at 12. I see, I'm so proud of myself when I see the derivatives going from negative to positive. It's not the correct answer. Questions are more complicated than you anticipate. So, now listen, if you are helped, it doesn't matter whether you're ADP or a Tuesday job, you're dismissed, go to ADP classroom and do the exit thing.